Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very good job of convincing people around here that IDS is really about policy, not matching signatures. The problem is in the hardware world, people are still stuck on signature matching. So there's a bit of motivation that I will skip over here. And the other thing she pointed out is I forgot to include a what is an FPGA slide. So let us begin with what is a FPGA, which is the basic tool that I'm using. And these are field programmable gate arrays. They're basically designed to be general purpose reprogrammable ASICs. So what happens is you have a little functional unit and a register embedded in a bit-oriented circuit switched network. So it's a statically switched network that's used to realize basically arbitrary circuits. This can be an arbitrary 4-input function and a little logic block. And then you have tiles of these. And so you'll have thousands of these little simple logic elements. And it's actually mostly the interconnect that's why they're so expensive, because they can range in cost from under $10 to over $2,000 to $3,000, depending on the size of the FPGA. Just in terms of comparing them with processors and ASICs, FPGAs have basically ASIC-level I/O bandwidth. Processor I/O bandwidth to physical world is horrid compared to an FPGA. The NRE costs of an FPGA are much better than an ASIC. ASICs cost a huge amount to build. ASICs aren't reprogrammable. And FPGAs, however, cost a lot more per part. So the general use of FPGAs is where you would use an ASIC, but you don't have the budget to develop an ASIC and you don't have the volume to justify it, or you need this reprogrammability, which the ASICs don't offer.
What NRE again? Sorry.
Non-recoverable engineering, the $30 million price tag it takes to do a custom chip these days. The couple of $1 million just for the mask set for the fab. So that's the big advantage of FPGAs. The big disadvantage is you still have to design the boards. I've gotten away with not having to do board design because I'm using somebody else's. These days, board design is becoming as bad as chip design. When you have these boards with 14 layers and the wires might as well be considered waveguides. So this is joint work with Vern Paxson and Chema. Chema developed the basic concept and the software implementation. Vern developed Bro, and I'm building the hardware. Oh, and jump in anytime with questions. Additional contributions, Nick McHugh and Greg Watson are the ones that developed the board I'm using. A lot of influence from Stuart and Dan. Funded by NSF, NHS, DOE. Opinions are my own, not the funders. This is work in progress. The mechanism works. We've tested the mechanism in software. The hardware is currently under construction, but their mechanism is simple enough and enough of the hardware is done that I know it will work. It just needs to get built. So the IDS problem, the HardLANs problem, I'm going to go light on these in this audience. And the big thing is how we actually propose using hardware to make Bro intrusion detection run at line rate gigabit. And I believe policy, but Helen says you've been indoctrinated. So the goal of this work is start with a policy-oriented intrusion detection system, full IDS, Bro, and use a mechanism to convert it to a high-rate intrusion prevention system. So it's inline. So rather than monitoring all packets pass through, able to process data at 2 gigabits per second, and using low-cost hardware acceleration in a commodity PC. We want a part cost for the board to be cheap. We already have that. And it's based on two key observations. All traffic must pass through the intrusion detection system, but most traffic doesn't need to be examined by the intrusion detection for a large set of reasonable policies. And the key technique is process 90% of the packets with a simple, imprecise hardware filter and less than 10% in software. And we absolutely must have hardware acceleration just simply because you take a gigabit Ethernet, you're sitting in line on that. That means your PC, just to pass packets in and out, will have to be passing 4 gigabits across the PCI bus and 4 gigabits across the memory bus, even if everything's staying in the kernel. And most PCs don't like it. And then once you want to do any memory-based computation, it gets worse, because if you have minimum-sized packets, you have 4 memory accesses per packet on a DRAM if you want to do a random access, because DRAM's just so bad on the latency. So we must have hardware acceleration if we want to run inline. So IDS is policy. Like what we'd love to do for BitTorrent is log. If it's in the local cache, we redirect the cache. If it's not local cache, cache it. This is all just an example of just how a security policy, BitTorrent, also affects performance when you cache, how your internet usage bandwidth is. Security at a high level, copyright violations, you want to catch and enforce those, because as a company you may be legally liable if your employees are doing something. Security is not just about keeping attacks out, but it still includes keeping attacks out. If something violates the protocol, you want to block it. So it's obviously, this is a huge, hard, annoying problem, even with the enterprise link. And the other bit of motivation, which I assume you guys are all pretty familiar with by now, is that we've got a problem that this needs to be embedded in the network. That if you look at the outside world, you can only enforce a policy on your perimeters. If you can't see it, you can't analyze it. If you can't analyze it, you can't enforce it. And our existing ones, and there's check paths, unchecked paths, which you cannot monitor or make assertions about, and control data and the control plane running things. The problem is, as we are undoubtedly familiar with, the big bad firewall perimeter is not very useful in this context because you miss so much information. Because once one attacker gets in, OK, now we have the insider attack problem, and this is a very nasty situation. And in general, in a lot of the work that myself and others are focused on, is you assume the attacker is an insider, and you start pulling your hair out in frustration. And the end host is really great at preventing attacks from going in, but not so good at preventing attacks from going out, because too many applications run at system level. Even when the ones don't, there are too many ways to escalate to system level. And once you escalate to system level, you can get out. The TCPA-based stuff, I forget what Microsoft is calling it these days. But the what? NG-spec. Changes more often than I can remember. NSCUM. Yeah, isn't that? Yeah. That's trying to address this issue by adding in basically a second perimeter down here that will hopefully work even when this perimeter fails.
I have a question about what you refer to by the control plane.
The control plane is that which is in making the decisions about policy. So for the firewall, it's the actual firewall software. For the system, it's the antivirus program. Once you penetrate the system boundary, you kill the AV. That's standard operating procedure these days. Thus, our focus has been on what could we do security-wise at the Ethernet switch. We're at ICSI network security people. We aren't host security people. I'm a lousy programmer to begin with, and I can't understand Windows. It's too complex for me. I can understand bits on a wire, so that's why, admittedly biased, that's why we're doing network, is we understand that space better. But the obvious thing is this is just such a much harder problem because cost really comes into play. When you're dealing with one corporate firewall, who cares about the $30,000 firewall box when it costs you $2,000 a month just for 100 megabit pipe to the internet? Cost matters a lot more internally because that per month you can buy gigabit switches for your internal structure. So the local area network just has massively more data rates, massively bigger. And so if we want to think about running intrusion detection in the LAN, we have to deal with gigabits. Network intrusion detection, most of the time you can get away with a lot less, but the LAN you have to be gigabit, and you have to be much cheaper. I don't know of any company that's trying for a $3,000 gigabit IDS system. It's a much harder problem. And so what our strategy is a very simple hardware accelerator on a conventional processor and a conventional IDS.
So I know very little bit about the TCA platform, Advanced Telecommunications Architecture Platform. Wasn't one of its goals designed to make it easier to build these kinds of things?
I haven't looked. I don't remember that platform. I don't know details. The problem is it's just data rate.
No. So, yeah, ATCA it's more than an individual box. It's basically a hardware specification for basically saying here's a very high-speed bandwidth bus. And now you can anyone can build line cards or processor cards to that. They slide in, and it's got exactly the kind of high flow throughput that you'd want for doing these sorts of things. I mean,
I'm not familiar with that.
Okay.
I'm sorry. The big problem is just it's not building the card. It's what do you do with it. That these days we actually do have that. It's called Ethernet. Everything's Ethernet. As long as your device speaks a gigabit Ethernet, you can just plug it in anywhere in the network.
I guess is the innovation in we can use an FPGA platform to do this at line speed, or is the innovation someplace?
The innovation is that by combining hardware and software, you can do it at line rate, with the notion of 90% of the work is done in simple, brain-dead hardware that throws up the 10% of the packets it can't handle to the full software decelerator. So it's doing this hardware-software co-design bit and making the hardware be very simple primitives, just a couple of table lookups. So that's the big innovation, is doing that, turning security into 90% header-based table lookup. So that, I hope, answers your question. So Bro is this IDS that Vern did that's structured already both around policy interpretation and around filtering. That the notion is you've got the initial network interface, you have the initial filters of what you're analyzing. That should reduce the amount of traffic you see going into the event engine, which does the low-level protocol analysis, and then the policy interpretation on top. So why are we dealing with Bro apart from Vern having developed the system? It is operationally used. This is critical. Early traffic in the connection is often the most important for the policies. That for some protocols we need to analyze the whole stream, but for a lot of them it's setup that counts. And also, since it's policy focused, it supports our demented worldview. So the other thing that I'm using is this board developed at Stanford that's primarily as a teaching platform. What it consists of is 4 gigabit Ethernets, a quad Ethernet PHY, a single large FPGA, 2 2-megabyte SRAMs, and a PCI interface to the host. And this is PCI, not PCIe, so this is a fairly narrow pipe. The existing design that they did at Stanford is some teaching thing, but also a 4-port Ethernet NIC. So the packets come in, get buffered in one of the SRAMs, copied across the PCI bus for receiving, for sending, receive, buffered internally, and sent out. And the internal data paths are actually, in the logic in here, 2 gigabits per second, because they're running at half the Ethernet byte clock, but 32-bit wide. And this makes it easy to meet timing and relatively easy for me to shove in new modules. I've already modified this design extensively to make research easier. So why did I do this? Well, it's big enough to be interesting, but it's small enough to be reasonable that the big cost is the FPGA. DigiKey, gray market, says $600, which means if you're seriously building it, you could probably spend $400 or less per FPGA. The memory is just enough to be interesting. 2 megabytes of usable SRAM is my entire memory budget on the hardware. But it's small enough to be reasonable that the memory cost, again, from DigiKey is $60. And it's tightly coupled to the host, that the host interface doesn't change because there's already Ethernet drivers. So from the host point of view, any host software just sees an Ethernet card. So the key observation, though, is that all traffic must pass through the IDS, but only a small traffic amount needs to be examined. So for SSH, and this is roughly the policy that Chema deployed for SSH in software. So you log all connection attempts. Bro tends to believe in when in doubt, log everything. If it's repeated password guessing, which you can see very early on, you block at the offending source and log it. If the new destination for a particular host, if there's too many new destinations in a particular amount of time, you want to log that. That's unusual. If there's a known attack in the connection setup, you block it, log, and report. And then when the connection terminates, you log the approximate traffic volume and the termination time. In order to implement this policy, you only need to actually examine connection setup, have a sample of the bulk traffic, and connection termination. That's all that's needed to implement this. So what can we do as a filtering mechanism to use this? So that's what we've developed, is this new notion into Bro of the shunt. It's an inline element that replaces the packet filter. And the big difference is that packets can be re-injected from the event engine. So a packet comes in. It goes through a programmable filter that's based only on packet headers. The host, the connection flags, and can do one of 4 things. You can forward the packet on out the other interface. You can drop the packet. You can sample the packet to allow Bro to do monitoring. Or you can shunt the packet to Bro so that Bro has to make its decision and then re-inject it. So when Bro is analyzing a protocol, it's able to act as an IPS. And each match, so you filter on host, connection, and the static headers, has a priority, and you select the highest priority match. And the IDS can add and remove entries from this table. And that's what you need. So extended Bro to do this. So you have new API calls and default behaviors. And you have to change the analyzers as well. So for example, the SSH analyzer was changed to, once the connection is set up, forward the traffic on. This is now a good connection, whitelist it. And part of the real key is that you have 2 components, the hardware component and the software component. The hardware component looks things up in the table and then can either drop forward or shunt it up to the host. The software layer in here, however, assumes that this layer can make errors. As long as we have single-sided error, that is, errors cause packets to go up the stack, it's fine. So we design for single-sided error. And this is very easy for hardware because it's just memory lookup. So what it is the packet comes in, You look up in the connection table, the connection header, the address table, source and destination IPs, the port table, static table for ports, and static filters for packet headers. So all SYNs, fins, resets get analyzed. And then you just take the action of the highest priority, and that's all the table does. So it's this very simple mechanism that gives us this ability to say, OK, this connection's good. I don't want to see it anymore. OK, this host is bad. Blockade him. But also, since the packets go up through the hardware or up to software by default, it's, OK, this is an attack in progress. Drop it on the floor. This is very easy for hardware. And by assuming that the hardware has errors, it makes life easier, because the hardware doesn't have to be perfect. The software viewpoint is the shunt the tables are infinitely large.
Is it open to a possible attack where the attacker tries to loop through to eject things from the cache? Presumably there's a limited amount of space you have for policies in the shunt.
Attacking the cache is, if you can't spoof packets, it's really easy because we just blockade your IP addresses.
Right,
if you can spoof packets, you can try to thrash our cache, but we use attacker unpredictable hash functions to begin with. So you don't have to brute force the cache.
I mean, sort of in a similar line. I mean, so inside of a LAN where you effectively have some kind of source address authentication, because you sort of know what belongs there or not. Maybe this works. But this is the classic Ceph architecture, and the 6509s at the edge, it is well known as a good way to bring down your BGP process by thrashing the cache.
Yes, thrashing the cache is a concern. However, we've found that if you can't spoof packets, we can blacklist you. If you can spoof packets, the cache eviction is actually under software control. So the packets that are missing in the cache are the packets you're sending, so you can clog up the analysis, but it won't affect the authorized streams once they've been whitelisted.
Right.
Cache attacking.
Pretty good denial of service.
Yes, it is a significant denial of service worry.
I guess the question becomes, so for the 2 megabytes of SRAM or something you've got, how many connections does that give you?
With 64K, 32K active connections plus another. One thing that we've observed is that 1 megabyte of memory is enough to track the external hosts for LBL. So you don't need a very big cache for the addresses. I'd like the cache to be a little larger, though. I'd really like about a 4 megabyte total cache. We are worried about cache thrashing. We are addressing the Crosby-style cache hotspotting, though. We don't worry about that because that we can engineer out. But cache thrashing is a concern. But as long as we can identify if you're just brute forcing the cache, you're probably in a position where one of the things is spoofing packets is getting a lot less effective these days. So in terms of a zombie blowing us away, a zombie could just saturate the link to begin with.
But the issue is that yeah, I mean, there are a lot of different ways to generate that kind of traffic, and typically even, if different ports, different destination addresses.
As long as the traffic remains under about 20% of a gigabit, we're okay, as long as the spurious traffic can be discarded quickly in software.
Okay.
Because
I guess the question is, how long does it take you to recognize that a single IP address is a hot sender, and then blacklist based on IP address alone?
That would probably be pretty quickly in the policy analysis. That's not stuff I'm addressing on the hardware side. That's up to software to decide. Question?
I have a question. So what kind of policies can can you enable here? Can you do any kind of content inspection would be part of the question here? Is it mostly about the connection analysis?
It's mostly connection analysis, although we have a scheme for HTTP that allows us to do content inspection of the flow control while skipping content inspection of the large transfers. We aren't building that into the hardware yet, just simply because there's limited memory and time. But so this is something we've considered, the ability to skip over into a connection and resume analysis. So it's skip the next K packets and then pick things up. Because HTTP, you've got these large transfers interleaved in the control stream. And so you want to skip you don't want to do the deep content inspection of every single GIF because you'll just go crazy. But it'll allow you to skip over that and then resume the control traffic. So effectiveness against a non-malicious input is very good. Only 23% of the packets need to be examined by Bro with a reasonable policy set. SSH, this works brilliantly. SSH policy, you only have to do the session headers. HTTP, we have this problem of the current analyzer is doing a fairly deep inspection, and as a result, basically has to look at 90% of the traffic for HTTP. The option we've considered is forward N. So for N packets based on sequence number, you allow it through. This allows us to drop from about 90% examining to about 70% examining, but it's still very high. That doing this style of examining really doesn't buy you much. The other thing that really buys us a lot is 50% of the traffic LBL doesn't have analysis tools for, because you've got BitTorrent, you've got all sorts of crud. And as a result, this works brilliant on those. So it works really good in the wide area network context. It should work even better in the LAN context, although we haven't come up with a good policy yet. I'm looking at setting up some Windows test beds so that I can actually get a good policy for Windows file sharing. I don't know of one. There is a huge limitation of this approach, and that's it offloads the packet transport and the preliminary processing, which would overload a commodity PC. But it doesn't actually reduce the CPU load on the Bro host all that much. And once we thought about it, it made sense because Bro already is focused around spending most of its CPU time on the interesting traffic. That filtering and then the event engine will end up on the SSH, just drop all the data. So it ends up having to read in the packet, but all it does is just a tidbit of analysis and then forgets the rest. So one of the interesting things is this approach doesn't buy you CPU performance. It only buys you performance on the memory and the peripheral bus. In terms of doing it with hardware, the key is that hardware, make it simple, make it faulty. Fixed memory, fixed table, static computation with single-sided error. That errors always result in packets going to the host, never packets being allowed on the wire. And so we use this software layer to provide a limited capability, while the hardware we're using fixed caches. 64K entries for IP addresses, so we can be blocking 64,000 simultaneous offenders with basically no performance penalty at all. So a good-sized botnet, but not a huge botnet. A trick that you can use is a 32-bit encryption to act as the tag index for IP addresses. This is a trick we developed in our Usenix paper. It basically effectively doubles the number of entries you can have in an IPv4 cache. For connections, a 1 megabyte connection table which gives us 32,000 entries, which is actually reasonably good for network traffic. I'll give you a slide on that in a sec. And if there's no entry, it's go it up to the host. And the shim has to reprocess all packets. It has to go, was this a cache miss or not? And then if it's cache miss, it has to reinsert the evicted entry using whatever policy the software does. As I said, this hardware is so simple, it doesn't even bother doing cache evictions. It's up to the host to decide on a cache policy. That's how dumb it is. But this actually, unfortunately, the smallest for this data run is 64K. This was before we really had a notion of what the hardware target was going to be. But even a 64K two-way associative cache has a miss rate of 0.02%. So, and this is for LBL's access link. So on a real internet access link, 32K, 64K simultaneous connections is good enough to make sure that most of the traffic gets correctly processed. And of course, bigger caches are better, higher associativity better. Better replacement policy, though, seems to be the biggest win. Least recently used will improve your cache misses by an order of magnitude compared to random replacement, just simply because you don't get a lot of problems. LRU really works on networks. So implementation, this hardware stuff is already done. I took the initial CNET design, which is a quad port MAC that's in gray. I modified it so that each MAC output, now instead of just being able to take a packet from the host, can take a packet from 4 other locations. So I have 5 output FIFOs. I modified the memory controller for the Scratch SRAM to support 5 reader writers rather than 2. This is a round robin. And then the big thing I added in was a thing in here that I called the splint that sits between each MAC and the arbiter that reads packets from all the MACs and forwards them on to the host. The splint buffers the packet, buffers a single packet, extracts the headers, has some decision-making logic that it's up to the user to implement. This decision-making logic can then route the packet onto the host and or route the packet to any or all of the MACs. And routing to the host, it has to wait. But as soon as it starts routing the packet to the MACs, it then reads in the next packet. So since these paths are at 2 gigabit, for packets that are internally routed, packets that don't go to the host, it's very easy to get the full bandwidth. While still having plenty of room to make a decision, because you can actually start to make a decision once just the headers are extracted. And as I said, once you begin routing the packet out, the next packet gets read in. And this is really designed as a very generic building block for packet processors. It's easy to do, line rate. I've got a test functionality that just has this register and scratch memory that says which way did the packets go and sends it out, and just a little program to peek and poke the memory. Rewriting capability, I currently don't support, but it's pretty easy as long as you don't want to do insertion or delete, because the packet's already in a buffer. Once the packet's read and completely, you can use that port to read and write packets. And I want to add a bit to add in and delete VLAN tags. I don't have that currently, but that seems really useful. Simply because if I want a 48 gigabit forwarding plane, I call HP and buy a switch. But with the VLAN tagging, Ethernet rewriting, etc., now I can turn that 48 gigabit forwarding plane into something interesting. All other information is common with the CNET, and this is actually part of the net FPGA distribution, or it will be. So this will be useful for others as well. There's a big run. planned, I believe, in September. So in September, these boards should be widely available. One of the nice things is it also keeps the software side. So I've run this with Click just fine. It just looks like an Ethernet card. I've hooked up my desktop through it. Apart from there is one minor bug in the board itself. It only runs at a gigabit. It doesn't work at 100 megabit. So this is a clocking issue. So in terms of hardware, I've done this RNet infrastructure. I've done the table layouts. I have a key address permutation for doing the IP cache. Unfortunately, it's currently not robust to an adversary. I need to redo this function. And basically, I was hoping to actually have some of the tables done on Thursday, but I've got the reading of the address table. I don't have the routing yet. I already have an API in Click, so it's easy to write a software module that processes packets and can peek and poke to the memory. So I've passed packets, hooked my desktop through this, passed packets through, and then reloaded the configuration and wondered, oh, wait, I forgot to remove my desktop so that it could work again. Latency appears really good. It should be easy to get about 300 microseconds of latency through this infrastructure. As a hardware person, I'm going, that's an eternity, but I know the network people don't care. So the hardware is not complete, but looks to be really, really close and really, really doable. That in terms of utilization, the RNet structure uses all the memories on the FPGA, but only about 50% of the resources. So there's a lot of leftover logic for people to do their own thing. So future work that we're considering using this for, well, we want to complete it and actually deploy it on IXI's LAN. We're going to deploy it in the LAN first just simply because it can mess up fewer people when only a few people are behind it. A couple of years ago, I think I talked about, did I talk about the worm detection using TRW here?
I think it was talked about.
Yeah.
Yeah, you did.
But I'm going to put that in the hardware as well, just simply because it's really nice and I've got enough memory for it. This wouldn't be on the same instance, so you'd either be running it as the shunt or TRW. But a nice little proof, this adds nothing to the research, but is a real nice proof of existence to the network crowd going, here, put this functionality in these Ethernet switches. One thing, others are looking at parallelizing Bro with load balancing, because a lot of Bro's work is on a per connection basis. So when you have, that says that you should be able to make a cluster, and there's a group up at Lawrence Berkeley Labs that has an old 6-year-old cluster that they're trying to run parallel Bro on. And one of the interesting things is the shunt is already close to being able to do routing, especially with VLAN rewriting and MAC rewriting. Why not use that as a load balancer for a parallel IDS? Because it allows the parallel IDS all of the benefits, but we have a problem at LBL. LBL wants to go to 10 gig. And there's no way you can do the kind of load balancing you want on a PC at 10 gig. You're going to need some sort of hardware front-end device to do the load balancing. So this is one thing that we've been just thinking about. The other thing that we've been thinking about is, hey, this might actually make a nice little forwarding plane for the Zorp router project. Especially since you still have the host. So if it's a IPv4 packet with no options and it's in the cache, you route it. Otherwise, you throw it up to the host. And one of the things that we thought about, we aren't sure if we'll build it, but we thought about, is that use a gigabit Ethernet switch as a backplane. So you take 4 boards, stick them in one chassis, connect a total of 8 ports to the outside world, and 8 ports to a commodity switch. And now you have an 8-port switch with a full-rate backplane. is the switches are great backplanes. So this is one thing that we've thought about, but we don't know if we'll build yet. So conclusion, though, is this simple, cheap and simple hardware architecture you can couple to a conventional IDS. And you really can make a intrusion prevention system out of an IDS that doesn't melt the memory bus. Looking only at headers. And the big key is look at only headers, and you do an imprecise cache with a single-sided error. The scaling is at a limit, however, for this style of IDS without going parallel on the back end. Because the front end we can now do faster, but now it's the back end that's the bottleneck. Don't really know yet what we can do policy-wise in the LAN. It's an open question. It's one that I hope to work on in the future. And another thing is another open question, are there other interesting hardware hacks to accomplish with this cool little platform? I think there are, because it's just fast enough to be cool and interesting. So that's the talk itself. So questions, comments, random rants? Am I totally bogus?
So you said the hardware is in progress right now.
Yeah.
Can you tell us a little more about that status?
OK. Let's put up the screen just so I get a little more space. So the status is, thank you, is I've got it to the point where I've got this little block in here that reads in the packet and makes the decision. This little block right now, so decide whether to go host or back around. This little block right now is just basically a dummy. I've got it able to read and write to the memory, and it's reading and writing to an address table that the host is writing. So I've got, so of the tables, so I can do the header. I can do the table lookup. So I've got the IP table lookup done, and I need to do the connection table lookup and the port table lookup. So the infrastructure is in place, header extraction done, table lookup IP done, connection port not done, and the routing out. I was hoping to have it working on Wednesday, but it's there's a bug in my code. So it really is in the really, really close stage. Because the rest of the infrastructure to do all the internal packet routing, reading and writing the memory, reading and writing it from the software host, that's all done. And what I'm doing for testing is I have my host off on the net, going through the board, and then the packets that go to the host go to a click module that reads and writes them out and sends them on the way. This is working. This is able to read and write to the memory here so that I can do the tests of, OK, let's set this table entry. Let's erase this table entry. So that's the status.
Were you asking about the Verilog or the boards and actually getting your hands on some?
I'll follow up on that.
In terms of actually getting your hands on the boards, it's Nick McCune's doing another run in September. I've basically a beta board. Well, it's an alpha board. There's like things soldered on.
Although he's very willing to actually, the whole thing was set up originally so that students not even at Stanford could actually log in remotely and do experiments on here. And so maybe the corporate university world interaction becomes a problem, but he is very open to having outside people. You can come and play with the stuff right now if you want.
And also there is one of the boards, I've got two of them. One's on my desktop, one I'm setting up in the Deter test bed, so hopefully in a month it will be usable for anybody who's willing to fill out the one piece of paperwork to get an account on Deter. So the hardware's actually in really good shape. It's just my stuff that's not working.
Simple matter of programming.
Yeah.
Thank you, Nick.